Let us do the supplementary chapter of vectors. We are going to learn scalar triple product. Let A, B, C be any three vectors. Then vector A dot vector B cross C is called a scalar triple product. This B cross C is a vector and this dot product gives a scalar answer. That's why this is called scalar triple product. And this can be written as A, B, C with commas in between, or without commas also we can write, and within square brackets.
Let us see the geometrical meaning of scalar triple product.
Geometrical meaning of scalar triple product is it gives the volume of a parallelepiped. What is parallelepiped? A solid body of which each face is a parallelogram. Let us take this as vector A, vector B and vector C. We know that vector B cross vector C is a vector which is perpendicular to both B and C. B cross C is a vector perpendicular to both B and C. And the projection of vector A onto vector B cross C is vector A dot vector B cross vector C divided by magnitude of vector B cross vector C. This gives the height of this parallelepiped. Magnitude of B cross C gives the area of the base. And volume of this figure will be area of the base into height.
If we multiply the height and the area of the base, magnitude of B cross C will get cancelled. So we get A dot B cross C. Therefore,
Parallelepiped. The parallelepiped is equal to vector A dot vector B cross vector C and its absolute value sign, because volume has to be a positive quantity. Now the next point is A1I. If three vectors are given in component form, say A1I plus A2j plus A3k is A vector, and vector B is B1I plus B2j plus B3k, and vector C is C1I plus C2j plus C3k. Then let us see how to calculate vector A dot vector B cross vector C. Determinant and expanded. First row components of A vector A1, A2, A3. Second row components of the second vector, and third row components of the third vector. Determinant gives the value of the scalar triple product. And then the next point is, in a scalar triple product, cyclic permutation of the vectors is allowed. We can write this as BCA or CAB.
this can be proved easily using the properties of determinants. By interchanging the rows twice, the value of the determinant is not affected.
It doesn't change the value of the scalar triple product. The next point, scalar triple product dot. In a scalar triple product, dot and cross are interchangeable. So we can write A cross here and dot here, but remember brackets for A cross B. Therefore, if we put brackets for B dot C, it is wrong because this is a scalar and this is a vector. We cannot find cross product of a vector and a scalar. Therefore, the bracket should be written only for cross product.
This also can be proved easily using determinants. Cyclic permutation is allowed. It can be written as CAB, which is C dot A cross B, and it can be written as A cross B dot C. Dot product is commutative. That's how these two are equal.
And then the next point, a triple product. If any two vectors are interchanged, C and V are interchanged here, we get a negative sign. By changing, this can be easily proved using the properties of determinants.
Interchanging any two rows in a determinant will give you a negative sign.
Then the next point, in a scalar triple product, if two vectors are identical, the answer will be 0.
If we write the scalar triple product as a determinant, two rows will be identical. That's why it is 0. Or we may say there won't be any volume formed. Volume of the parallelepiped is 0.
If three vectors, vector A, vector B, vector C are coplanar, if and only if is 0. The scalar triple product is 0. What do you mean by coplanar vectors? All three vectors lying on the same plane. If all three vectors are on the same plane, parallelepiped, so volume has to be 0. That's how A dot B cross C is 0. This is an important result. Then the next point is coplanarity of 4 points. Three points are always coplanar because passing through 3 points we can always draw a plane. So here we are checking the coplanarity of 4 points A, B, C, D say. So we know the coplanarity of 3 vectors, the 8th point. So we will find any 3 vectors. Let us find AB vector, AC vector and AD vector. If vector AB dot vector AC cross vector AD is 0, then these 3 vectors are coplanar. If these 3 vectors are coplanar, the points are coplanar. A, B, C, D are coplanar. And point, checking the coplanarity of 4 points. Let us start exercise 10.5. First question, find C if vector A is equal to I cap minus 2j cap plus 3k cap and vector B is equal to 2I cap minus 3j cap plus k cap and vector C is equal to 3I cap plus j cap minus 2k cap. Let us find the scalar triple product A dot B cross C. We know that it can be written as a determinant. We will write the components of the first vector, then components of the second and components of the third. Let us expand this determinant 1 into 6 minus 1 minus of minus 2 into minus 4 minus 3 and plus 3 times 2 minus of minus 3 is plus 9. First term is 5, second term is minus 14 and the third term is 33. 48 minus 14 which is 24. Second question, show that the vectors A, B, C are coplanar. So let us find vector A dot vector B cross C. If it is 0, we can conclude that the given three vectors are coplanar. The first vector is I cap minus 2j cap plus 3k cap, and the second vector is minus 2i cap plus 3j cap minus 4k cap, and the third vector is I cap minus 3j cap plus 5k cap. The expansion is 1 into 15 minus 12, minus of minus 2 is plus 2, minus 10 plus 4, and plus 3 times 6 minus 3. The answer is 3. Minus 6 times 2 is minus 12, and 3 3s are 9. 12 minus 12 is 0. Therefore, the given three vectors, vector A, vector B, vector C, are coplanar. Question number 3. If the vectors I cap minus j cap plus k cap, 3i cap plus j cap plus 2k cap, and I cap plus lambda j cap minus 3k cap are coplanar. We know the coplanarity condition. Vector A dot vector B cross vector C should be 0. Let us write the determinant to find the scalar triple product. Components of the first vector, then components of the second vector, components of the third vector is equal to 0. We will expand the determinant. 1 into minus 3 minus 2 lambda, minus of minus 1 is plus 1, minus 9 minus 2 plus 1 into 3 lambda minus 1 is equal to 0. Minus 2 lambda plus 3 lambda is lambda, and minus 3 minus 11 is minus 14 minus 15 is equal to 0. Therefore, value of lambda is 15. Let vector A is equal to I plus j plus k. Vector B is equal to I cap, and vector C is equal to C1i plus C2j plus C3k. Then the first subdivision, if C1 is equal to 1 and C2 is equal to 2, find C3, which makes vector A, vector B, vector C coplanar. We know that the coplanarity condition is vector A dot vector B cross vector C should be 0. We will write the determinant for the scalar triple product. First vector's components 1 1 1. Second vector only I term is there, so 1 0 0. And C vector C1 C2 C3. C1 C2 values are given. We need to find C3. Let us expand this determinant. 1 into 0, first term is 0, minus 1 into C3 minus 0 plus 1 into 2 minus 0. Therefore, the value of C3 is 2. In the second subdivision, C2 is given as minus 1 and C3 is given as 1. Show that no value of C1 can make vector A, vector B, vector C coplanar. Let's find A dot B cross C, which is equal to the determinant A's components 1 1 1, B's components 1 0 0, and C's components C1 we have to find. C2 is given as minus 1 and C3 is 1. Let us expand this determinant. 1 into 0, first term is 0, minus 1 into 1 minus 0 and plus 1 into minus 1 minus 0. The answer is minus 2. Never it can become 0. Whatever the value of C1 is, this scalar triple product never takes the value 0. C1, no value of C1 can make vector A, vector B and vector C coplanar. 5. Show that the 4 points with position vectors 4i cap plus 8j cap plus 12k cap. We will take these 4 points as A, B, C, D. Second vector 2i cap plus 4j cap and plus 6k cap. The third position vector is 3i cap plus 5j cap and plus 4k cap. And the last point is 5i cap plus 8j cap and plus 5k cap are coplanar. And vector A. Let us find vector AB, vector AC. Vector AB is vector OB minus OA. 2 minus 4 minus 2i, 4 minus 8 minus 4j and 6 minus 12 minus 6k. And vector AC, position vector of the terminal point minus position vector of the initial point. 3 minus 4 minus I j and 5 minus 8 is minus 3j and 4 minus 12 is minus 8k. Vector AD is vector OD minus vector OA plus 0j and minus 7k. These three vectors. Let us do scalar triple product of these three vectors, which can be written as a determinant. Components of the first vector minus 2, minus 4, minus 6. Then components of the second vector and then the third. Let us expand this determinant. Minus 2 times 21 minus 0. Minus of minus 4 plus 4, 7 plus 8. Minus 6 times 0 plus 3. It is minus 42 plus 15 times 4, which is 60, and minus 18. 60 minus 60, the answer is 0. Therefore, vector AB, vector AC, vector AD are coplanar. If these three vectors are coplanar, the points, the given 4 points are coplanar. Proving the coplanarity of 4 points is an important question. Question number 6. Find x such that the 4 points A, 3, 2, 1, B, 4, x, 5, C, 4, 2, minus 2 and D, 6, 5, minus 1 are coplanar. Vector AC, and we will find vector AB, vector AC and vector AD. Vector AB is position vector of B minus position vector of A. We will do B minus A. 4 minus 3, 1i plus x minus 2j plus 5 minus 1, 4k. This is vector OC minus vector OA, which is 4 minus 3, 1i, 2 minus 2, 0j, minus 2 minus 1 is minus 3k. Then vector AD is OD minus OA, 5 minus 2, 6 minus 3, 3i, 5 minus 2, 3j, and minus 1 is minus 2k. Let us do the scalar triple product of these three vectors. We will write the determinant. First row AB vector 1, x minus 2 and 4. Then components of the second vector 1, 0, minus 3. Components of the third vector 3, 3 and minus 2. Question that these 4 points are coplanar. Therefore, the scalar triple product has to be 0. I equate it to 0. Let us expand this determinant. 1 into 0 minus of minus 9 is plus 9 minus x minus 2 times minus 2 plus 9 plus 4 times 3 minus 0 times x minus 2. 9, 7 times x minus 2, which is 7x minus 14 plus 12. 9 plus 14 plus 12 is equal to 7x. Therefore, x is and 26 plus 9, this total is 35. 7x is equal to 35. Therefore, x is 35 divided by 7, 5. Answer is x is equal to 5. Vector A plus question number 7. Show that the vectors vector A, vector B, vector C are coplanar if vector A plus vector B, vector C and vector C plus vector A are coplanar. Then scalar product, if these three vectors are coplanar, then scalar product of these three vectors should be 0. A plus B dot B plus C cross C plus A should be 0. Vector A plus vector B dot, we will use distributive property. We get B cross C plus B cross A plus C cross C, which is 0, plus C cross A is equal to 0. C cross C is 0. And now we will distribute this dot. A dot B cross C plus A dot B cross A and plus A dot C cross A. Now let us distribute the second term, vector B. We get B dot vector B cross vector C plus B dot vector B cross vector A and vector B dot vector C cross vector A, and it is equal to 0. In the first two steps, we have used distributive property. We know that if two vectors are identical, the answer will be 0, 0, this is 0, so this is 0, this is 0, this is 0 and this is also 0. Write the reason. Two vectors are identical. Therefore, we are left with two terms, vector A dot vector B cross C plus vector B dot vector C cross A is equal to 0. This is A, B, C. And we know that we can change the vectors in cyclic order in scalar triple product. So A, B, C. Vectors can be changed in cyclic order. So we get 2 times vector A, vector B, vector C is equal to 0. Therefore, vector A, vector B, vector C is equal to 0, which implies vector B, vector C are coplanar if vector A plus vector B plus vector C and vector C plus vector A are coplanar. Example 30 is a similar question. Now we will do example 31. Prove that scalar triple product of vector A, vector B, vector C plus D is equal to scalar triple product of ABC plus scalar triple product of ABD. Let us take the left hand side. This is vector A dot B cross C plus D. This crossover addition. Let us distribute this crossover addition. We get B cross C plus B cross D. Now again distributive property. We get A dot B cross C plus A dot B cross D. And this can be written as ABC plus, and that is ABD, which is the right hand side.